Good morning, my name is Federica de Chiara, and I'm very glad to present at the IEEE Sensors 2021 conference. My talk is focused on the design of optical waveguide channels for 3D distributed tactile sensing. Tactile sensors with high spatial resolution have been widely explored and developed with application in different fields. The aim of this kind of sensor is providing realistic dexterous artificial manipulations. There are different types of sensors. The piezoelectric sensors present a good high frequency response and very high resolution in the order of 5 micronewton, but they are not able to measure static forces accurately, and they present relatively complex fabrication methods. Capacitive sensors are independent from temperature, present a high frequency response and dynamic range. However, they are affected by noise coming from straight capacitance and channel crosstalk. Resistive sensors are able to measure different quantities such as temperature, light, magnetic field strength, and deformation. However, they are unsuitable for long-term monitoring because of large time drift and temperature drift. Also, they present complex wiring structure, and they are susceptible to electromagnetic disturbance effect and humidity. Optical sensors are able to measure the variation of the properties of a light source following a change in the environmental conditions. They present very interesting characteristics such as electromagnetic immunity. They are safe even when used in hazardous environment. They enjoy low life, good accuracy, manufacturing simplicity, and high reliability. Many optical tactile sensors have been developed even with high spatial resolution, but their integration into devices with no planar surfaces is still a huge challenge. To address this challenge, we are going to present an optical-based sensor applicable also to complex 3D shapes. The prototype we are going to present is based on the sensing principle of total internal reflection. An optical waveguide is made by a core with a refractive index N1. The core is usually surrounded by a different material called cladding with a different refractive index N2. In order for the light to be transmitted through the optical waveguide, N1 must be higher than N2. From the Snell law, we can get the relationship to calculate the critical angle theta. Theta is the angle between the light propagation direction and the perpendicular to the interface between core and cladding. When this angle gets higher than the critical angle, then total internal reflection occurs, which means that the light is successfully transmitted through the waveguide. When a force is applied on the waveguide, a deformation is applied to the cladding and to the core, and therefore it can happen that theta is not higher than the critical angle anymore, and therefore total internal reflection is not satisfied. In this case, the light is lost and emitted outside of the waveguide. The prototype I'm going to present is based on this sensing principle. So when a force is applied, the light modulation is measured to detect the applied force. On the left-hand side, we can see a multisplitter configuration, which has been developed to get a multisplitter waveguide configuration which has been developed to increase the spatial resolution. In fact, the light is injected into the input channel, can be transmitted through the different branches of this configuration, and reach the 8 output channels, which are independent sensing elements, which can be pressed, and the light modulation can be measured to detect the force applied on each branch. On the right-hand side, we can see the manufacturing process. The multisplitter configuration has been CNC machined on a polymeric material with refractive index equal to 1.4. A soft material with higher refractive index is injected into the mold. And then a thin layer made by the same material as the CNC, the substrate, is applied as a cover on the prototype. Then the prototype is left curing for 24 hours. Here we can see how the multisplitter configuration can be is adaptable to complex 3D surfaces. So following the same manufacturing process as presented before, a soft material can be injected onto this substrate, and therefore different waveguide channels made by soft material can be pressed and can determine a light modulation at the output. A simulation analysis has been carried out using the commercial available software OptiStudio by Zemax to guarantee an equally split light emission from each one of the output channels. So the light propagation can be easily, unequal light propagation can be easily obtained in the case of a simple configuration, such as the one shown in A of a single splitter. However, when the configuration gets more complex, such as the one shown in C with 8 output channels, these getting an equal, similar light transmission through the old branches get more challenging. However, we can see in the graph, in the right-hand lower corner, that we got a similar light transmission on the 8 output channel, with a difference of just around 3% on the output 4 and 5. Here it's shown the final prototype, which is characterized by a compact size. On the right-hand side, we can see the light transmission through the waveguide configuration. And below, we can see the experimental setup. So a green light source has been used to inject light into the input channel. The light is transmitted through the multisplitter waveguide configuration. And a calibration force sensor has been used to measure the force applied or on each output branch of the splitter. The force is applied using a thin metal rod, and the light modulation of the 8 output channel was measured using a camera. The results are shown here for each one of the 8 output channels. We can see that the channels present a similar force response, in the range between 0 and 0.3, 0.5 Newton. The mean value can be considered as the calibration trend for each one of the channel. In conclusion, I presented an optical phase array sensor made by polymer materials, presenting a multisplitter structure. Just one light source is enough to inject light into the input channel of the device, and this allows the miniaturization and help to reducing the costs. The 8 output channels corresponds to 8 independent sensing elements, which can be pressed and can determine a light modulation. Each channel can detect forces in a similar range between 0 and 0.3, 0.5 Newton. The prototype shows a compact design. It's low cost, can be simply manufactured, and it's adaptable to non-planar surfaces. As future work, it's possible to increase the number of sensing elements and reduce the distance between them to increase the spatial resolution of the device. Thank you for your attention.